Okay, so my name is Dr. Miloš Rydval, and I'll be talking a little bit about the impacts of climate change on forests. So just kind of to give a brief overview of what I'll be talking about, we'll be talking about climate change and the context of climate change. After that, I'll introduce some basics related to tree rings. Also, I'll talk about climate reconstruction and future climate prediction. Then I'll talk a little bit about the effects of climate change on forest growth and productivity, and I'll give a few examples of forest response to changing climate. I'll primarily be focusing on examples from Scotland, but I'll give some examples from other locations as well. Then we'll talk a little bit about the complex interactions of various climatic as well as non-climatic factors, and then some of the implications for forest ecology and for forest management. So let's talk a little bit about climate change and specifically temperature increase. So we know that for about the last 150 years since the Industrial Revolution, there's been an increase in temperatures globally, and that increase has reached almost close to 1 degree since pre-industrial times. And the way we know this is due to various meteorological stations throughout the world, which record temperature and other climatic information. So what we can then look at is if we combine many of these records together across the world, we can get a representation of how temperatures and how climate has been changing in the recent past. Now, the problem with this, or the limitation of this, is that the further back in time we go, the spatial representations of sites and locations with meteorological records decreases. So, and also we have fewer and fewer pieces of information as we go further back in time. So, if we look at some of the longest records that are out there, one would, for example, be the Central England temperature record, which goes back pretty much, with some reliability to the late 1700s. However, there's information from, for example, historical documentation, which allows the extension of that record even further back in time, back to the mid 1600s. But of course, this is a bit of an exception, and most records in the world are 100, 150 years in length. So there's a limitation there. But if we combine all these together, we can have some representation of changing climatic conditions, changing temperature over time. Now, we know that this is primarily in the recent history, or the recent period at least, this is primarily related to increases in atmospheric carbon dioxide concentrations and increases in greenhouse gas concentrations, which are primarily linked to the activities of people, anthropogenic activities, and emission of these greenhouse gases. So what we see, actually, there's one long record which goes back to the mid-1950s and is based at Mauna Loa Observatory, which is on Hawaii. And there's this record going back 65 years or even longer with changing atmospheric carbon dioxide concentrations. So what this shows us is this increasing trend from around 315 in the time when records started to be kept to about a little bit over 400 parts per million in the last few years. So an interesting feature of this record is this sort of cyclical increase and decreasing cycle of carbon dioxide in the atmosphere, and primarily this is related to the northern hemisphere summer, when there's a lot of productivity in terms of vegetation growth, and this then absorbs some of the carbon dioxide that's in the atmosphere, and then in the winter time, northern hemisphere winter time, some of this gets released back into the atmosphere, for example, through decomposition and other processes. So you see the importance that vegetation can have, and how big the effect can potentially be, even on these interannual sort of timescales. So, and of course, in relation to climate change, we could be talking about many other aspects, for example, weather extremes or shifting precipitation patterns, sea level change, and so on. But we'll primarily just focus on some of the basics. So at this point, what we really should talk about first is what growth actually represents, or how we can represent growth. What are the aspects and what are the factors that affect tree growth and forest growth, tree growth, and how these factors come together in order to give us some productivity over time. So what we see here is this conceptual model called the linear aggregate model, which essentially represents growth or productivity as a combination of certain factors. And these factors are, R here being the tree ring width. Then age is an important factor, which as a tree gets larger and larger, the amount of growth or the amount of sort of productivity gets sort of splayed out, or gets divided over larger and larger surface area. So as the tree gets older and bigger, the same amount of sort of productivity has to be is essentially spread over a larger and larger surface area. So that's one factor to take into account. Another is climate. So in certain locations where climate or some climatic factor like temperature or precipitation, soil moisture, is an important determinant of growth. If conditions are more favorable or less favorable, this is something which will show up in sort of the productivity as well. Now, after that, there are two factors which are somewhat related but distinct from each other. This disturbance, D1 and D2, endogenous and exogenous disturbance factors. And essentially what these represent is endogenous disturbance factors are any factor originating from within the forest community, which affects the growth in some way. So this can be, for example, a tree or dying, some mortality occurring, and then essentially the surrounding trees within there will respond to this greater availability of resources. So you might have more light, more space, and so on. And as a result, they will respond. They will grow essentially more than they otherwise would if this tree that died was actually still there. So that's the endogenous disturbance. What we also have is another factor called exogenous disturbance. And the idea is the same. Some agent introduces a disturbance in the sort of forest stand. And this can be, for example, related to fire. This can be a windstorm event, which either damages or essentially removes some of the trees which are there, and then again the remaining trees will respond accordingly. And then the final sort of aspect here is noise. This is essentially all other variability in terms of growth. So if you look at two trees growing next to each other, they may not necessarily respond exactly in the same way to the same environmental conditions. So even within one tree, you can have differences in different parts of the tree, for example. So if you try to get some representation of growth, and you take, for example, a sample of the tree and to look at how much productivity has occurred in over time, this can differ quite, to a certain degree in different parts of the tree. So that's all these important elements. And one thing to mention here is that because climate is one factor which affects growth, we can, if we take into account all the other aspects, we can actually get some representation of climate using growth and tree information of growth from trees. So now at this point, we could talk about a little bit about the sensitivity of growth. What aspects growth can be sensitive to, and what are some growth forcings. So we can talk about, for example, the principle of limiting factors. This essentially states that a biological process, such as growth, cannot proceed faster than is allowed by the most limiting factor. So essentially what this means is that in any given area, there might be, or in any particular case, individual tree, there might be one predominant factor which is affecting growth, and other factors which may not necessarily be limiting to growth. And another sort of concept is this concept of the ecological amplitude. This essentially is related to each species growing and reproducing over a certain range of habitats. So it's not surprising that certain tree species, for example, can grow in certain environments, but they may not be able to grow in others. And now, if we're interested in looking, finding out something, for example, like a climatic information, then it makes sense to go to locations where growth is limited by this factor. So, and where tree growth is sensitive to this. So this might, for example, be the top of a mountain, at very high elevations, where summers can be shorter, and generally, if conditions are warmer, then more growth occurs. If conditions are cooler, then there is not as much growth occurring. And if you are in contrast to that, if you're in an environment where there is not this distinct sort of limiting effect of these type of variables on growth, then you might not be able to detect these type of signatures. Now, so how can we actually get some of this information, and what are some of the approaches for doing this? Well, one approach is called cross-dating, and this is essentially related to the expectation that trees in sort of seasonal environments will produce a certain amount of wood, which will be distinctly separated from the productivity of the next year and that of the previous year. And this is mainly related to changes that occur in the formation of the wood and throughout the growing season, and then changes towards the end of the growing season when the structure of the wood changes and with most species in temperate locations, we can actually visually see this separation from one year to the next as distinct bands of rings. And so essentially what we would expect to see is this lighter early wood transitioning into a darker late wood towards the end of the growing season. And essentially we would expect to see one ring for every single year. And however, this is not always the case, because there can be, for example, years when growth conditions are not very good, and as a result of that, a tree may not necessarily produce a ring, which means that in that particular year, there will be no record of growth in this tree ring record. So, and actually, the reverse is true as well. For example, if you have quite favorable conditions at the start of a growing season, and then transition to relatively unfavorable conditions in the middle of the growing season, the growth might potentially decrease or stop, or there might be a signature of this in the tree ring record, and it may seem as if there is a boundary. However, then if conditions improve later in the growing season, growth may return back to normal, and it may seem as if there are two rings within 1 year. So the way to get around this is by looking at the samples and the tree ring signatures and the tree ring patterns of many trees within one area, which should be reacting and do react to the same sort of environmental factors. And as a result of this, we can cross-match the rings going back in time, and we can find instances where, for example, one tree did not produce a growth ring, and we can correct for this. So in this way, by comparing with the many trees, we can ensure that each ring is assigned a calendar date in an absolute sense. So this is called cross-dating, essentially. And now, so this cross-dating can essentially be used by dendrochronology, or essentially a discipline where we look at the tree ring record over time. And this can be one way to, for example, look at the climate in the past and reconstruct climatic history. So what this does, as I mentioned, we have this process of pattern matching of trees and their rings. And as a result of this, as we build up more and more samples, we can create a chronology or representation of average growth conditions within a particular area over time. And the nice thing about this is that if you do not only need to rely on samples from living trees, for example. So if you have some relict wood, a sample from a historical building, for example, with a wooden structure, and this sample or this relict wood originates in this area where you already have some record of growth, you can essentially use this cross-matching approach this cross-dating approach to match up and build up this chronology going further and further back in time. So it's essentially like putting together puzzle pieces. And of course, if these trees are located, and this wood is located in a location that has a climatic limitation, so if the growth is predominantly determined by temperature, or for example by the amount of moisture availability, then you can create a representation. You can use this information to create a representation of this climatic variable going back in time. So in this way, it's essentially possible to create a record of many centuries or even thousands of years going back in time. And the nice thing about tree rings is that they are really exceptional when it comes to representing the resolution that they offer, and you really can get information for every single year. And the reason we can actually get this type of information from tree-ring records is by relying essentially on an assumption called the uniformitarian principle, or uniformitarianism, which essentially in a nutshell can be summarized as the present is the key to the past. And this essentially means that the conditions that are the response to conditions in the present time, so response of growth and tree growth to particular conditions, was the same in the past as it is in the present time. So this means that the trees will respond in the same way to particular environmental conditions in the present and in the past. And using this, we can create essentially a relationship between what the tree is doing, the tree growth is doing on average, and some climatic variable that the growth of these trees is responding to. And by establishing this relationship, we can then use the tree-ring record to give us information about this particular climatic variable. So here you see, for example, one climatic record from the UK, from Scotland, which goes back about 800 years. So this is one record, and this essentially is equivalent to essentially one meteorological station in one location in terms of the information that this can give us. Of course, this is also, there is some uncertainty related to this information. And then if we use many of these reconstructions, many of these tree-ring records of some climatic variable, and we put them together, we combine them, we can get some sort of representation of average conditions, for example, of temperature going back in time, and we can essentially represent climatic conditions for the whole hemisphere or for the whole globe. We can go back several thousand years potentially using tree rings. Now we can then potentially extend this idea of uniformitarianism and essentially not only say that the present is the key to the past, but also that the past and the present are the key to the future potentially. So this is where statistical modeling comes in, which essentially is a way of trying to predict the future climate, essentially, or get some representation or some estimates of how climatic conditions may evolve and develop moving into the future. Now, the importance of tree rings and tree ring informations and tree ring reconstructions is that they can help to essentially train and test and sort of improve the performance of these models, because if these models were just relying on the relatively recent period where we have instrumental information for trying to establish how well they behave, how well they represent actual climate, this would just give us a very limited temporal window in which to test these models. But by developing these longer reconstructions of climate going back in time, we can then test these models on much longer time periods. So that's very useful. Then potentially this can make them more accurate and potentially give us better predictions of future climatic conditions. So what we see here is some of these statistical projections of future climate. This is from the IPCC, or the Intergovernmental Panel on Climate Change, which is a scientific body under the United Nations, which is tasked with providing assessments of climate change and representing the knowledge that we have, or sort of synthesizing and providing information about the knowledge that we have about climate change. And you see here there are some projections in terms of different types of scenarios related to the levels of greenhouse gas emissions, carbon dioxide emissions in the atmosphere that we might expect to see in the future. So there are some more optimistic scenarios, as well as some pessimistic ones, and a few in between, related to how much the magnitude of the emissions that will be occurring in the future. And as a result of that, we then see changes in temperature going into the future based on these scenarios. So again, some more optimistic scenarios and more pessimistic scenarios with several degrees temperature increase going into the future. Now, there are also some longer term projections as well based on these different scenarios going forward several hundred years, and the corresponding temperature changes as a result of that. But of course, the degree of uncertainty is quite considerable and increases here in these particular circumstances. So, taking all this into account, what does this actually mean for the future of forests? And this, what can we actually say about future development of forests and what will be happening? So, for example, will conditions improve? Will they worsen? Will they not really change very much? And really the answer to this depends on factors such as the environment that you're looking at, and also individual species that you want to talk about. So rather than talking about all the different options and combinations of what could be, how forest and tree growth can potentially respond to these changes, we'll just have a look at a specific environment or specific species, Scots pine, Pinus sylvestris, which has a very broad range from across Eurasia, from the far east of Asia all the way to Scandinavia, parts of Western Europe. And what we'll actually be doing is talking in relation to the species in one location, and this is that will be in Scotland. And this essentially represents the northwest limit of the growth of Scots pine in Europe. And so actually the interesting question there is why is this the limit of growth for this species? Why is this the edge of its range, essentially? And part of the answer to that has to do with climate. And we'll talk about that in just a second. So one interesting factor to look at is looking at environmental conditions over time. We can say that the climate in the past has already changed quite significantly, and the environmental conditions have changed very significantly in different locations. But here, looking at a pollen record from northern Scotland, this essentially gives us a representation of the vegetation and the vegetation types and the representation in the environment over time. And the advantage of these long pollen records, from this particular one being from a peat bog in northern Scotland, is that they provide information going back several thousands of years. So the way to read this essentially is looking at the top here, the top part of the graph. That's the more recent period. So we start here at about 2,000 years ago, and then as we go further and further down, we go deeper into this pollen record, or this profile, this core, and we can go back almost back to the last ice age, so close to 8,500 years ago. And what we see here, well, there is a representation of a range of different species, but if we look at Pinus sylvestris, Scots pine here, we see that actually in the history, in this historical record over thousands of years, there have been very dynamic shifts in terms of the representation of these species and the representation of Scots pine in these landscapes. And we see actually that the proportional representation of the species was quite high in different periods in the Holocene. And as we get closer and closer to the present, we see that this representation of the species decreases quite significantly. And if we are to look at the present day, we would see that really there isn't really very much left in the landscape. So really the main point here is that these are quite dynamic systems and not static. That they did not look the same in the past as they do in the present times. So if we actually were to look at a profile, a peat profile in northern Scotland, we see that there's a layer of essentially stumps, in situ stumps and root systems. So this essentially means that these are trees which grew in this location. They were not transported here by some mechanism. They grew here, then they died here. And so we see that at some point in the past there were forests or trees growing here. But if we look at the surface, there are no trees or forests in this environment at the present time anymore. So that's quite stunning. And really, then we could ask, what is the reason? Why do these trees not grow here anymore? Why are there no forests? And one of the answers to that is essentially that the environment is a bit too wet. We have a sort of a moss and peat layer at the very top, and the conditions are not very good for tree growth or for Scots pine growth anymore. But of course, going back in time, at some point the conditions were more favorable to growth than they are today. So we see that actually these type of changes have already occurred naturally in the past. And of course, as a result of climate change and anthropogenically sort of induced climate change in the present period, we can potentially expect also some quite dramatic changes to the environments that forests can grow in and trees can grow in. And so actually looking at Scotland in more detail in terms of the climate, we see that essentially Scotland is one of the wettest places in Europe, particularly western parts of Scotland, which have very, very high rates of precipitation, the amount of rain essentially, and it's very wet. And one of the reasons this is the case is that we have an oceanic climate in this environment. And what we also see is this very strong sort of gradient going from west to east, where there's not as much precipitation in the east, and the environment is a bit more continental in character. So sort of looking at this, what are some of the predictions in terms of how the climate will develop, or how climate change will potentially change weather patterns and specifically in terms of precipitation? Well, some of the projections and predictions are that the winters there will become wetter, and the summers may become drier, and then there might also be more intense precipitation events. So more intense storms, for example, more higher amounts of rain over a certain period of time, greater precipitation amounts. So one of the reasons for this is that as the atmosphere warms and the air becomes warmer, it is able to hold more moisture. And so potentially this northwestern part of Scotland might actually become wetter in the future. Now, if we actually look at what might happen in a certain, in this type of environment, let's say that we have an area which doesn't necessarily support a sort of closed canopy forest. The tree growth is more separated. There you have individual trees growing there, but these are still regular trees. Now imagine that this environment becomes wetter. So what we might see is that essentially in that type of environment, these type of trees may not really be able to grow properly anymore. Normal Scots pine trees will not be able to grow here because one of the reasons for this is that the soil may be waterlogged, may contain quite a lot of water, and these are conditions where in these anoxic conditions that roots of these trees cannot really breathe, and that is not very good for in terms of the growth of these trees. So, however, what we might see is still the possibility of stunted forms of these trees, in this case called bog pine, which are able to tolerate these wetter conditions to some extent. So we might see some type of replacement. But then imagine if the conditions become even wetter, then we might see sort of the overgrowth of moss and a conversion to marshes and wetlands, and which essentially do not support or may not support growth of trees at all. So we know that something like this has happened in the past over certain time scales, but of course the question is, how will the environment respond in the future, and especially on relatively short time scales as a response and as a result of climate change. Now, another aspect to consider is the tree line. So when we're talking about the tree line, this essentially is the limit or elevational limit, if we're talking about an alpine tree line, above which a particular species of tree, in this case, cannot really grow. Now, if we look above the tree line, there might still be a zone where essentially some stunted forms of a species can still grow. So these may not look like conventional trees. These may look more like bushes, for example. And then as you go higher and higher up the mountain, you reach an elevation beyond which these trees cannot grow at all, the species cannot grow. So that's the tree species line, beyond which you have the alpine zone. So no growth of trees there. And then moving down in terms of elevation, there's a zone between the timberline and the tree line where growth is possible. However, it may not necessarily be a closed forest. It might be more of an open environment for where trees grow a bit more separated. And then, as you go lower down, below the timber line, then you have forests, really closed forests. Now, the important thing to note here is that as conditions become warmer and as the climate becomes warmer, the temperature essentially is the main factor, or one of the main factors controlling this tree line and the position and the elevation of the tree line. So as conditions warm, we can expect a migration or increase in elevation of the tree line, and so essentially we might see trees starting to grow in locations where they were previously unable to grow. And there is already evidence of increasing tree line elevation in certain parts of the world. But it's also worth mentioning that the position of a tree line can be distorted and can be modified by other factors, other non-climatic factors, for example. And actually in the case of Scotland, and especially northwestern Scotland, the tree line position and elevation is lower than it otherwise would be, and this is a result of wind stress and essentially wind exposure, which lowers the tree line elevation. So here's actually one example of a tree line shift. We're looking at subarctic Sweden. This is an area near Lake Torneträsk, and we see here a comparison between almost 100 years ago, 1912 and 2009 on the right here. And we can actually see this shift, this change over time from essentially the tree line elevation being somewhere here to, looking at the more recent period, an increase in tree line by more than 100 meters, essentially, which is quite stunning. And we see that there's a greening, increased vegetation growth on these slopes here, which before were quite bare and did not support tree growth or vegetation growth. So this is quite a stark change. And one, for example, we can also talk about Siberia, another location where this might be happening. But there we see more of a latitudinal shift in the tree line, going polewards, farther north. And essentially this can be described as sort of a shrubification of Siberia. And what this also does, one important factor, is that we see a change in albedo of the surface, and albedo essentially is the reflectiveness of the surface. So we see that here on essentially several 100 years ago, we had conditions where this surface was much more reflective, especially when covered by snow, for example, in the wintertime. But now we see that in the more recent period, if this area is covered by shrubs or trees, then these will be able to absorb more incoming solar radiation, and rather than reflecting shortwave radiation back away from the surface, this will be absorbed and re-radiated as long-wave radiation, and then potentially contribute to some degree to warming within the atmosphere. So this can be seen as a sort of a positive feedback, where the warmer it gets, the larger essentially the area that is covered by shrubs and forests and vegetation, which changes the albedo, and this allows it to absorb more incoming solar radiation, and so you have this feedback, positive reinforcing feedback mechanism. Now, looking back at the Scottish example, we can also look at some other locations and parts of this environment with relict forests. And this particular example shows a relict forest, essentially, which was preserved, probably covered in peat for some time, re-exposed more recently, and we see that again in this location there was a forest growing, a tree growth. Now the important thing to note here is that this location nowadays is almost 200 meters above the present day tree line. So this tells us that at some point in the past conditions were different in such a way so as to be conducive to the growth of trees in this particular location. Again, where no trees can grow in the present day. So we see these type of dynamic changes in the past, and essentially these I believe were present here, or were growing here around 5,000 years ago, or even more. So we're dealing with quite long timescales in this sense. Another important factor to note is wind, potentially changing wind conditions, windiness patterns, and for example, what we could see is wind and windstorm patterns changing, and wind intensity also changing, potentially increasing. And what this might do is essentially locations or sort of tree stands which were previously able to withstand certain loadings of wind or wind stress may not be able to do so anymore. And as these start to become disrupted and perhaps some parts of these forests start to die off, or there's a removal of these forests, the integrity of these forests can be compromised, and they may then become even more susceptible to wind damage. And when we talk about wind damage, this can be, for example, related to wind prune, where there's a sort of a mechanical action of the wind on the surface of the branches or sort of leaves or needles, for example. We can see something like wind snap, where a tree can be, if the wind intensity is high enough, it can be snapped in half. Or, for example, wind tilt, where the tree may be sort of partly blown over, or wind throw, when sort of the tree is entirely blown over and uprooted. So, so this is really a very important component which can affect disturbance patterns in forests and the landscape. And we can see also that in some instances this can affect the tree morphology. So in this particular example, we see that the form of the tree is more streamlined, so that it can better deal with the incoming sort of wind, predominantly coming from the left side here. There can be other morphological changes, and in terms of, for example, the windward side of the stem being having essentially thinner rings, less wood produced on that side, and thicker rings on the windward, the leeward side, and thicker rings to be able to provide more structural integrity and to support, so that the tree can actually withstand some strong winds. Now, in some parts of Europe, and particularly the Northwest, there's one of the important determinants of not only wind patterns and wind strength, but also, for example, temperatures and precipitation patterns, is the so-called North Atlantic Oscillation. And this essentially affects conditions over relatively long time periods. And so, we might potentially want to ask, well, how will future conditions change as a result of this phenomenon? So let's talk a little bit about it. So the North Atlantic Oscillation is essentially an atmospheric phenomenon related to the dynamics of the atmosphere. And this essentially is a representation of pressure patterns in the Atlantic. And what we generally tend to see is a low pressure system over sort of this area close to Iceland. And then also we see generally a higher pressure system, typically off the coast of Portugal and Western Africa. So what we actually say when we talk about what we're talking about when we're talking about the North Atlantic Oscillation is essentially the strength of this pressure difference. So the relative difference of this low pressure system and the high pressure system, typically measured as the pressure over Iceland in terms of this low pressure system here, and commonly as a pressure over the Azores or Lisbon, for example, part of Portugal. And if we look at the difference between this gives us a representation of the North Atlantic Oscillation. And so we can look at this over time, and we can look at the relative difference in pressure. So if the pressure difference is greater, that meaning that there's a stronger high pressure system down here and a sort of lower pressure here around Iceland, then we have a positive essentially positive North Atlantic Oscillation index. And if this pressure difference is smaller, so the low pressure is not as low and the high pressure is not as high here, then we have more of a negative, neutral or negative North Atlantic Oscillation Index. Now, the reason this is important is that if we have more positive NAO index conditions, meaning that this pressure difference is greater, stronger, this essentially allows the weather systems and the jet stream and the weather systems associated with that to more easily sort of directly access Europe, and we have this essentially this flow across the Atlantic directly into Western and Northwest Europe. And I should mention that this mainly affects the winter time climate and sort of meteorological conditions. So when we have this positive NAO situation, in the wintertime, we see more moist air and warmer air being transported to Northern Europe and Western Europe. And so we have warmer and wetter winters generally. And conversely, around the Mediterranean area, we tend to have these cooler and drier conditions. Now, when the NAO index or the NAO is in a more negative phase, this essentially means that this pressure difference between Iceland and the Azores is lesser, and as a result of that, this creates sort of blocking meteorological pattern, and then essentially this the jet stream and the associated weather patterns are diverted to the Arctic, and then essentially we have a flow of Arctic air moving to Northern Europe. So in the wintertime, this gives us cooler and drier conditions in this part of Europe. And conversely, we have generally warmer and wetter conditions around the Mediterranean. So the interesting aspect to note here is that in the last few years, or in recent years, there's been more of this positive sort of phase on average. And of course, then the question is how potentially will this NAO dynamic and this phenomenon respond to climate change? How will it develop in the future? Will we have more positive or more negative or more neutral conditions? And mainly, it's a bit difficult to tell, and we're not entirely sure right now. But there's a lot of work going into trying to answer some of these questions. But perhaps there is some indication that maybe more of these positive NAO situations might be more common in the future. So here, just very quickly, look at the association between NAO and the NAO index and winter temperatures. So we see that when this index is higher, we tend to get these warmer conditions in Northern Europe. At the same time, we see when this index is higher, we have more precipitation in Western and Northwest Europe and drier conditions around the Mediterranean and the Iberian Peninsula, Northwest Africa. And also we see that the wind intensity is greater, so there's more, so the wind strength and wind patterns are stronger when we have a more positive NAO situation. So one aspect to talk about as well is, I was talking for a while about this relationship potentially between growth of trees in a particular location, where, for example, a particular climatic variable is limiting to growth. And this idea of this uniformitarian principle about the response to those conditions in the present time are linked to those in the past. Now, actually, in recent years or recent decades, there's been some essentially some studies have noted that there has been, in some locations, in some areas, either a weakening or a loss of tree growth response to temperature in the latter half of the 20th century. So what this essentially means is that the relationship between temperature and growth has not been stable and has either weakened or has diverted altogether, meaning that as temperatures continue to increase, we do not necessarily see a corresponding increase in tree growth. And there have been a wide range of potential, suggestions of what could be causing this, and everything related to, for example, the temperature-induced drought stress, which essentially means that as the conditions become warmer and warmer in a particular area, the tree growth may not be as sensitive to that variable as it was in the past. So essentially, if we have a location at the limits of growth of a tree, and the conditions become warmer and warmer, this temperature may not be a limiting factor to the same degree or in the same way that it was in the past. There are also some suggestions that we might be seeing a nonlinear interaction between tree growth and climate. So essentially, the relationship between growth and climate may not strictly be linear, and we may not necessarily see a corresponding increase in growth to particular combination of changes in climate conditions, and that's related to potentially other factors becoming more important as a limiter to growth. Also, there are some ideas about what the trees are responding to and what we are measuring and what we are comparing it with. So there's this idea that tree growth response in these temperature-limited environments are more related to maximum daytime temperatures rather than average temperatures or minimum temperatures. And we actually see that minimum temperatures have been increasing at a higher rate than average or minimum temperatures. So potentially one possible reason for this disconnect. There's also a global dimming phenomenon, sort of a hypothesis, which is related to higher amounts of aerosols and particulate matter in the atmosphere, leading to lower availability of light reaching the surface, and therefore that these trees or this vegetation may be reacting to changes in the availability of incoming solar radiation compared to changes in temperature. Or other factors may be important. For example, in some areas, quite heavy local and regional pollution may have an effect of potentially stressing the growth of trees, stressing them in such a way so that they begin to respond to this pollution stressor, and their growth may be limited by this. And they might not then respond to a particular climatic variable that they responded to in the past in the same way. And also the way that we obtain and get information from these treeing records and some methodological sort of end effects and other methodological issues could potentially also to some extent be responsible for what we are seeing, this disconnect. Now, really when talking about forests and the climate, we also have to talk to some extent about the role people and of humans in essentially modulating or modifying the environmental conditions, which then may interact with how the forests grow and the climatic conditions in potentially complicated ways. And here we have one example of the Brazilian Amazon, and essentially a snapshot of the same location in the 1970s, then in the late 1980s, and then about 20 years ago. And we see that there's been sort of increasing deforestation, which is leading to a more and more fragmentation of these forests and of the rainforests in this area. And what we then see is increased edge effects, for example, and changes in, for example, soil structure, and also the way that the forest responds to environmental conditions. So one of the changes that we may then see is that if you have a closed rainforest, this is essentially a very wet environment, and it's very difficult to start a fire in this type of environment. However, as you start to break that up more and more, and this environment starts to dry out more, it becomes easier to start fires. And so while in certain areas the forest fires may have been very rare in the past, in undisturbed areas of the rainforest, we may see as that more fragmentation is leading to it becoming easier for forest fires to start in these areas. And if we look at the dry season of 2019, there really has been an unprecedentedly high rate of forest fires and the areas affected throughout the Amazon. Now, of course, these systems to some extent have some built-in resilience, and they are able to sort of withstand and buffer some of these changes. And for example, one of the reasons that actually it is so wet in the Amazon is that a lot of this moisture and water is retained within the vegetation, and through evapotranspiration, you have that's one reason why there's quite a lot of condensation and then rain in these particular areas. But of course, as you start to disrupt this environment more and more, you may at some point reach a tipping point, and where essentially you get into this feedback mechanism, a positive feedback mechanism, where you break up the forest more and more, conditions become drier, it becomes easier for forest fires to start, and essentially that can affect and destroy further a larger part of this rainforest. So you get into this cycle. And the important thing to note here is that at some point it may not be necessarily possible to transition back to and regrow this rainforest and go back to the conditions as they were in the past. But rather you might have conditions, both climatic conditions and of course the environmental conditions changing in such a way so that there might be a transition to forests which are more drought resistant and more seasonal forests, for example, or even a savanna type environment rather than a sort of this closed rainforest environment. So even though there is some built-in resilience and some self-regulation, this is limited, and it's possible to reach a point beyond which this environment, this sort of ecosystem is not able to sustain itself. Now, we can look at some other recent examples of extensive forest fires. For example, the example of Scandinavian fires in the summer of 2018, last year, where essentially, and also in the summer of 2019, very widespread forest fires throughout Siberia. And in the Swedish example, we see, or in the Scandinavian example, we see that in that year there were record high summer temperatures, essentially a heat wave for a very unusual heat wave for quite a long period of time, which resulted in very hot and dry conditions over the summer. And this then led to an unusually high number of an extent of forest fires. And what we saw then was that by the middle of the summer, by late June, something like 40 or 50 fires covering around 250 square kilometers, stretching from the northern part of Sweden beyond the Arctic Circle to southern parts of Sweden. And in the Siberian case, very large areas of Siberia, essentially 3 million hectares, affected by wildfires. And one of the effects this had was that this very negatively affected air quality in large parts of Siberia, for example. Now, there are other potential complicating factors to take into account. And one of those, again, is disturbance, not necessarily related to natural processes, but disturbance related, for example, to human behavior, human actions, which may, for example, include things like logging and removal of forests. And if looking at the example in Scotland, we can see that in different parts of this environment, even locations that are not so far apart, we see that there's a record of disturbance related to human actions, logging specifically. And we see specifically that in the eastern part of the country, there was a period 150, 200, 300 years ago of some degree of logging. But compared to that, looking at the western parts of the country, the rates of logging were much more severe, much more extensive. And essentially what you see is that not only is climate an important determinant of what happens with these forests, this type of behavior is sort of another element which must be understood in order to get the larger picture of what's happening. And actually looking at growth and biomass production in comparing the western part of Scotland with the eastern part, we actually see and detect this record of sort of additional growth or higher growth in the west than we do in the east as a result of larger areas of forest being removed, and then again the trees responding to these more open growing conditions. So we see that there is a very long and complex history of climate and human influence in these type of environments, which can vary quite significantly over space and time. And another factor in this environment is related to especially if you're looking at potential strategies for regrowth and replanting some of these forests, this may be complicated by certain factors. For example, deer populations, which are quite high throughout the UK and in Scotland, and the deer populations eat saplings, or they like to eat saplings. So this makes it very difficult to regrow trees and forests in certain areas. So we can talk about some of the direct impacts on forest ecology, specifically in relation to Scotland. So as a result of climate change, this, and the changes that we might see, this can potentially affect the functions and some of the services that forests can provide. And specifically with the amount of precipitation and amount of water in the environment, there's a possibility that we might see in this part of the world wetter winters and drier summers. And also what we might see is warmer summers. So potentially this might lead then to increased productivity in certain parts that might benefit from longer summers and warmer conditions. But also at the same time, if conditions become too warm and there is not enough water, not enough precipitation, not enough soil moisture, then the soil moisture conditions may become limiting to growth. And for example, it's possible this could happen in the eastern parts of the country. So in terms of forest productivity, we might see a possible shift in the areas that are suitable for the growth of forests, and also areas that are suitable for reforestation and afforestation efforts. So for example, if wind stress increases and wind exposure is a major limiting factor, this may affect some areas and may make it difficult to grow trees and reforest some of these locations. And also we might potentially see either elevation or latitudinal shift in the tree line position. So again, a shift in the areas where trees can grow and where they have a harder time growing. Also, we can see an increased overall productivity resulting from longer growing seasons with higher temperatures throughout the growing season, increased atmospheric carbon dioxide concentrations as well, supporting growth. But it's important to mention that the magnitude and the size of this carbon dioxide fertilization effect, or essentially increase in growth as a result of higher concentrations of carbon dioxide in the atmosphere, is quite uncertain, and it's not really sure how vegetation and tree populations will respond in the long term, and to what gains there might potentially be in that sense. Now, other factors may potentially become limiting to growth. For example, competition may become more important, water availability, or the soil conditions, nutrient availability, and so on. These are other factors which could potentially become limiting as other climatic factors become less limiting in the future to growth. Now, talking about some of the indirect impacts on the ecology of forests, we can, for example, talk about the health of forests, and we might expect, for example, that milder winters may result in a later onset of dormancy. So this means that some species could potentially not even enter dormancy at all, and so potentially this might lead to an overall decrease in the resilience of some of these individuals and some of these forest stands. And partly related to this is, for example, the pathogen and insect outbreaks and insect pathogen populations, pests. So we might potentially see, as winters become milder and the conditions become milder, this might potentially lead to larger populations of pests surviving throughout the winter, and longer and warmer growing season conditions, which might then lead to an increase in the number of life cycles of certain species in a particular year. And also, as a result of warmer conditions, higher CO2 concentrations, there might be more food availability for these pests, and the decrease in the time needed to mature, and also an increase in fertility. So some of the potential effects that might be seen. So looking at some of the implications for forest management, there are different options and different potential strategies for dealing with the uncertainties of climate change and the changes in environmental conditions that we might see in the future. And some of these options might, for example, include a larger, sort of a more diverse mix of species within forests to try to help reduce some of these the susceptibility of these forests to pests and pathogens over a certain area. Also, it might make sense, for example, to, in addition to mixing species, to also introduce a wider genetic base of a particular species and certain varieties that might potentially be more adapted to more extreme conditions. And for example, there might also be some possible consequences for timber supplies, some market prices, and insurance costs in the future. And really the main issue is that with forest management, it's necessary to plan long term. So this is quite difficult, and really some strategies there might be, for example, planning several decades into the future, or a century into the future, to look at analogs of climatic conditions that you might expect to see in the future in a particular location. So, for example, climatic conditions in Scotland may become maybe more similar to that of northwestern France today in the future. Looking forward several decades. So then it makes sense maybe to look at which species are able to grow in that particular environment and use that as an analog. So just to quickly conclude, we've seen that tree growth and forest communities respond to various environmental factors, but at the same time, they can also, to some extent, moderate and buffer the influences of these factors. And we've seen that climate change impacts can affect a wide array of environmental conditions, including temperature patterns, precipitation patterns, and intensity of precipitation events. Of course, there's changes in the carbon dioxide concentrations in the atmosphere. We may see wind and storm patterns changing, the frequency and the intensity of these events changing in the future, as well as some large-scale differences and changes to large-scale weather patterns and climatic dynamics in general. So the result of this changing global climate is that we might expect that these factors may affect forest populations in various ways, both directly and indirectly, in a wide range of ways. And of course, some of these may be predictable, others may be a bit more difficult to predict and may be unforeseen. Now, also, such factors are likely to influence the future growth, and we may see a shift in the species distributions in the future, also in terms of composition, and then changes to, in terms of insects, pests, and pathogens, their patterns and growth, and so on. Okay, thank you very much for listening.